All right, can you all hear me okay? Is the mic good? Okay. So I've been informed that there were 2 talks scheduled, but the other speaker hasn't made it, so you're all stuck with me for as long as I want. I hope you're ready. So I'm going to be talking about, actually I'm going to be announcing tokio-trace, which is a framework for scope, structured, and async-aware diagnostics in Rust. First of all, you probably are all wondering, who am I? My name is Eliza Weisman. I'm a systems engineer at Buoyant here in San Francisco. I've been writing Rust since 2015. I've been doing it professionally for almost 2 years now. I contribute to the Tokyo Tower and Linkerd2 open source projects. And some of you have probably seen my wildly popular Twitter account where I post stupid jokes and pictures of my cats. Okay, great. So you're probably wondering, why didn't I make another logging library, right? We already have a pretty robust ecosystem for logging. We have the log crate, we have the envlogger crate, we have the fern crate, we have the slog crate, okay. Well, first of all, I don't like to call it logging. I prefer to call it GNU/logging. That was a joke. What I actually like to call it is in-process tracing. We'll talk about what that actually means in just a moment. But in order to answer this question of why did I make another logging library, I'm going to start asking some questions of you in the audience. So how many of you are using futures? Raise your hand. All right, okay. Looks like a decent fraction of you. And so if you're using futures, do you get logs that make sense at all? Is it possible to figure out what's going on? Anyone? No. Okay, that's what I thought. Yeah. Asynchrony is hard, right? It's hard. It's an unsolved problem. But if you're writing a high-performance networked application, you probably need to use asynchronous programming. But it presents some pretty unique challenges in terms of diagnostics. In async applications, at least in Rust with futures, execution is multiplexed between tasks. And when tasks become I would say blocked here, but they don't actually block. When tasks need I/O to proceed, or when they need something from another task to proceed, they yield, and we start executing another task. And when the I/O that task requires becomes ready, we will switch back to the original task. And because we do this switching between contexts so rapidly, we can get log messages that are interleaved. We can get situations where we see the same log message a bunch of times because we have tasks that are executing on multiple cores. And it's just really hard to tell what's actually going on in these asynchronous systems. So what do we need in order to get usable diagnostics from these asynchronous systems? The way I see it, there are 3 main things that we need to be recording, which are context, causality, and structure. So context means that when we record an event that occurred, we need to know not just where in the source code it happened, but what was the actual runtime context around this event. For example, if we have a server that's processing some requests that are coming in, that context might include what client did this request come from? What were the request's method, the request path, the request's headers, and so on. In synchronous code, we can just read our logs in order and infer the context from the preceding log messages. But in asynchronous code, we switch between contexts as we begin executing different tasks. So our diagnostics need to actually record the context in the diagnostics. Second, we want to capture causality. What other events caused some event to occur, right? So if we have some task running in the background that's driving a DNS resolution or a database connection or something, what caused that background task to start? Or what request required that DNS connection in this example? In async systems, again, we can't really rely on log ordering to infer causality. So we need some way of actually recording that data. Finally, we'd really like to have structured diagnostics. Traditional logging is based on these text messages, and they're human readable. But it's much better if our diagnostics are machine readable. We can interact with diagnostic data programmatically, which I suppose you can do to some extent with textual logs if you use grep, right? So if you have some field that you want to see all of the logs where that field is equal to 3, you can just grep for 3. But you can't express more complex concepts that way. Like, say I want an inequality. I want equal to or greater than 3. What can I do? I can't really grep for that. Sure, you could start actually parsing those logs and treating them as type data, but that's a whole lot of work. It's really better if our diagnostics are actually recording typed structured data, and it never just becomes these text messages that require human intervention to understand. So I'm going to pause the slides for just a moment, and we're going to start with a quick demo, which I have prepared ahead of time. I have a terminal here. Oh, I need to actually stop presenting, switch to my terminal. Everyone see the terminal? No, they do not. Okay. Hang on just a sec. All right, do you see the terminal now? All right, and Harrison wants to join. I've been told that Adam is manually accepting everyone who wants to join the live stream. So I have an example that I'm going to be running here. This example is based on the library Hyper, which I'm sure some of you have used. It's an HTTP implementation in Rust. And this is based on an example from Hyper that is an echo server example. It's quite simple. So all I've done is I've taken this example and I've modified it very slightly. And what I've done is I've added some tokio-trace diagnostics to the example. So I'm going to start running the example. Sure. Is this readable now? Okay. So we already are getting something back from our server. I'm going to try and make this second terminal a little smaller so we can fit a little bit more on screen there. We see that we've gotten something back from our server, right? It's running and it has a bound local address. And so it's printed the local address that the server is listening on. And here we see that it's localhost and it's bound to port 3000. So what happens if we actually start interacting with our server? Send it a request. Can't type today. Can't type at all. Oh, my keyboard's a bit of an angle here. So if I send a request to our server, we see these diagnostics come back. And so now we see not only that we're running a server, but we have accepted some connection, and it's from this remote address, which is curl on some ephemeral port. And we have a request on that connection. The method is get. The path is slash. So we received this request, and then we sent back a response, and the body was try posting data to slash echo, right? So this formatter that we're seeing here, we have some scopes in it. And these scopes are indented, and everything that's indented here means that it's a child of some scope. So the request is a child of the connection, the response is a child of the request, the connection is a child of the server, and so on. Now, this is not probably a way that you would want to format your tokio-trace diagnostics in production, but for the purpose of this demo, I think it gives us a nice visual way of expressing that we have some nested scopes here. So the HyperEcho server told me we should post some data to /echo. Let's see what happens when we do that. So I'm going to go back to this terminal where I have curl, and I'm going to curl localhost on port 3000. And this time I'm going to request the path echo, except not like that. And I'm going to add a message body to my request. And curl-d means that curl knows that this is a post. So we're going to post some data to /echo, just like the server told me to. What happens when we do that? So now we see that we have a separate connection, we have a separate request, and that request has a different method and is to a different path, and that it had a different response kind and a different response body. So we can now see that we have this logical tree of scopes that own each other. And if we had some traditional logging, if we're just using the log crate, these lines would just all be individual textual messages. And if we were to send a great deal of requests at the same time concurrently, if all of you were to curl this echo server, you can't do that. It is not exposed to the internet. But if you were to, we might start serving some of those requests concurrently, right? Because I'm using a multi-threaded runtime. I have as many cores as my MacBook has to serve requests from. So we might be serving a whole lot of requests. We might be writing out some different echo bodies to each of those requests. And if we were doing that, we might see a big mess of logs here that wouldn't make sense. But because our diagnostics encode context and they encode causality, we get this pretty little tree. So I'm going to switch back to my slides now. Somehow. Computers are hard. Here we go. So I'm going to switch back to my slides. We've seen the demo. And the question we have now is, how does tokio-trace actually work? Unless there are any other questions, but I think this is the one that is probably on everyone's mind right now. And we're going to start answering, how does tokio-trace actually work with, what did I mean earlier when I said in-process tracing? Anyone here familiar with the concept of distributed tracing systems? These are technologies like OpenCensus, OpenTracing, Jaeger, Zipkin. Anyone in the house? Got a few distributed tracing fans in the house. Are you guys distributed tracing fans or not really? Okay. Right. So for those of us who are not distributed tracing fans, these tools are diagnostic tools for distributed systems. And they're designed around tracking contexts as they move between nodes in a distributed system so that we can correlate events that occur on one machine with events that occur on another machine. This works by, for example, when we have a request moving through our distributed system, we tag it with some kind of identifier, and we can track that identifier if all of the nodes in the system that are participating in the service of this request somehow forward that identifier. So we can track that context and we can correlate this machine did this thing in service of this request. And so we have this way of tracing through these distributed systems. So these tools are intended for debugging large-scale distributed systems. But the insight behind tokio-trace, and I think something that really informed its design at a basic level, is the idea that asynchronous applications are sort of like distributed systems writ small. Sorry. So you have tasks running concurrently that are sort of like individual nodes in a distributed system. You're no longer communicating by synchronously calling functions. You're now communicating through asynchronous message passing. You have some channels with which these tasks are interacting. And this is sort of like sending messages on the network, right? It's fallible, it's asynchronous, just like everything in the real world. So your asynchronous application is kind of like a little miniature distributed system that's running within one address space. And so a lot of the ideas in tokio-trace are drawn from this world of distributed tracing because the same concepts apply, I think, really nicely to tracing within a single process. So we have some core primitives in tokio-trace. We're based around modeling the world through the idea of spans and the idea of events. So what are spans? A span represents a period of time during which our program is executing in some context. So a span has a beginning and an end that are points in time, and then it has times when it was entered and times when it was exited. This means when we enter a span, this means that we are executing in that context. When we exit it, that means that we are no longer in that context. And we might exit and enter a span multiple times, but it will have started and eventually it will have ended. So it represents a discrete period of time. And here we have a little example of actual code for creating a span. We have the span macro. The span macro gives you back a span handle, which exposes a whole bunch of methods, one of which, the most important one, is that you can now enter this span. And the enter function takes a closure or a block. And inside of this closure, we execute some code. The code inside of this block happens inside of the span. And then when it finishes, we have exited the span. Great. Spans. So the other core concept is we have this idea of an event. And events are much simpler than spans. An event represents a singular moment when something occurred. This is pretty much the same as a log record in more conventional logging. Unlike log records, however, events exist within the context of a trace. So an event is located inside of a span, and it exists within this trace tree, so we can see the context in which it occurred. Similarly to the span macro, we have an event macro. This one is recording just the textual message that something happened, and it is at the info level, so it's not extremely verbose, but it's also not an error or a warning. We inherit basically the same levels of verbosity as the log crate for compatibility reasons. We'll get into that later. So here's an event. Finally, we have a concept of fields on both spans and events. Fields are how we record typed, structured data. A field is a key value pair, has a name, which is the key. The name is a Rust identifier. The value is a Rust primitive. We have a subset of primitives that are valid fields. We can also record any format debug or format display data as fields. And in the future, we might have arbitrary serialization for fields of arbitrary user-defined types. And tokio-trace lets us consume these field values as those types and not as just a string. So let's look at an example. This example comes from the real-world application of yak shaving. See the yak here? Okay, we're going to shave some yaks. This is a domain model that I think is very widespread. Lots of people have to shave yaks. So let's look at how we might shave some yaks. So to start out, we create a span. In this span, we're shaving yaks, so we call it shaving yaks. And we annotate it with the number of yaks that we're going to shave. We have a field called yak count, and it's the length of yaks, which is some list or array that we've got. And so we enter the shaving yak span, and then we loop over all of the yaks, right? So for each yak, we create a new span called shave, in which we're going to shave the current yak. And we annotate it with which yak we're shaving. And this span is nested inside of the shaving yak span. So anything that occurs within this span is considered to be part of the span, but also part of shaving yaks, right? Okay, so then we call this function, it's called shave yak, and we match on the result, and then we have some events. And based on whether that event or whether that function succeeded or failed, we have one event or a different event, great. So anything that happens inside of the shaving yaks function call is also inside of this span shave. So it's annotated with the current yak that we're shaving. Because shave is inside of shaving yaks, then everything that happens in this function call is inside of shaving yaks. So all of the diagnostics that this function emits record which yak we're shaving, how many yaks we're shaving, and which specific instance of this shave span we were inside of. Because if we're running the same code on n cores, then we have n separate shaving yak spans. And so we can track which individual context this occurred in. We might be shaving some number of yaks on one thread and a different number of yaks on another thread, so we have distinct field values, and so on. Finally, we have a component called a subscriber. There is supposed to be another word on this slide. I believe this is a bug in the presentation software that I'm using, because it's supposed to say that subscribers collect trace data. It just says collect trace. Sorry about that. Technical difficulties. Computers don't work. So we have this component called a subscriber, and a subscriber is the component that's responsible for actually collecting the data in a trace. You can think of subscribers as being somewhat similar to loggers in your conventional logging systems. Quite similarly to loggers, this is the extension point where you might implement user-defined behavior. So you get to set what subscriber is active at any point in the program, and that subscriber will be the one that collects trace data. It's an interface. We have a trait subscriber that you implement, and now you have a subscriber. So libraries or implementations can provide subscribers with wildly different behavior. You might have a subscriber that just prints traces to standard out. And as we already saw, there are a million different ways of doing this, depending on how you want to format your traces. You might have a subscriber that records metrics based on values. You might have some counters, or you might be doing some time-based profiling based on actually time-stamping how long we spent in given spans. You might have a subscriber that sends events to some external aggregator, or some tracing system, or to Splunk, or whatever log aggregation system that you might be using. So you can have all of these different behaviors, and the subscriber interface is designed to be very broad so that it's possible to implement all kinds of different behaviors on top of it. So how do we use tokio-trace? We've tried to make it as easy to use and especially easy to adopt as possible. A big part of this is that we want to be compatible with other libraries in the ecosystem that you might already be using. There are a lot of ways we've maintained this compatibility. So here are some examples of some of the stuff we can do. It plays nice with futures. In fact, it has been designed to work with futures from the ground up. It's tokio-trace, right? Okay, so we really want to be able to support debugging asynchronous systems. Futures are the building blocks of asynchronous systems in Rust. So here we have some example code where we have some future, and we're using some combinators to compose some functions onto this future. So we have an and then that we do if the future is successful, and then if both of these are successful, we just have the future completes. We have a map error that we do if either the future or the and then block returns an error. And here we're just recording that we are doing something or that the error happened. And then at the end, we have this new combinator instrument. Sorry. An instrument is provided by tokio-trace. It's actually provided by an external crate. It's built on top of tokio-trace. The crate is called tokio-trace futures. It's very imaginatively named. I came up with that. And so tokio-trace futures gives us this new instrument combinator on futures, also on streams. And instrument attaches a span to the future. So whenever this future is polled, we enter this span. For the duration of the poll, we execute inside this span, and then we exit it once the poll has ended. And this will happen as many times as it takes to drive this future to completion. So what that means is, again, here, everything that happens in any of these combinators, or in the future itself, or in the call to the do something function, is all inside of that span. And any subspans will last for their duration within that. So something else you can do is, a lot of you are probably using the log crate, right? It's pretty standard logging facade in Rust, and it is basic, like textual logging. It's not structured logging yet. So if you import the log crate, you use its macros, you can do something like this. You can say info, and then you have a formatted message. Great. Shut up, Adam. So I'm going to get on that. I'm going to talk about that later. I am going to talk about that later. So if this compiles, guess what else compiles? This. What did I do? What just changed? Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. So we have these macros in tokio-trace for instrumentation, and they are a superset of the log crates macros. Well, some of them are. We have some other macros. Like, obviously, log currently has no concept of spans, so our span macro is not a superset of its span macro because it has none. But we have info, debug, warn, error, and trace macros that support all of the same syntax as the log crates macros. So if you are using log right now and you want to adopt tokio-trace, what do you have to do? Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. Log, tokio-trace. Now, of course, you don't get all of tokio-trace's functionality if you do this, but it is the first step. And it means that you can switch tokio-trace in place of log, and your crate still builds. So then you can incrementally start to adopt some of tokio-trace's features. We can start adding spans to our code. We can start adding structured fields to some of these log messages. We might replace the foo and the bar in this formatted string with foo and bar fields. But we can do this incrementally. We don't have to break the world and rewrite all of our instrumentation points. just to try tokio-trace. Furthermore, we have a lot of other compatibility layers with existing logging infrastructure. We have adapters that let you record log messages as trace events. We have an adapter that lets you record trace events as log messages. So if you have some dependency, which is some library that you use, which is using log, you can consume the log records that it emits as tokio-trace events in your trace tree. Obviously, the library does not have tracing instrumentation itself, so the library is not defining any spans, but its records exist within your spans. I'm actually going to show a demo of this in just a moment. Similarly, if you want to be able to emit log instrumentation for users of your library, but you also want to use tokio-trace, we have an adapter to go in that direction as well. Finally, I want to take just a moment to talk about performance, because we're Rust programmers here. Performance is important to us. And our performance goal is that you should only pay for what you use. I'm going to take a drink and then. So any runtime instrumentation has some performance costs, right? If you're collecting any kind of diagnostic, whether it's printf or some extremely fancy metrics or tracing system, you're doing some work at runtime that you wouldn't be doing otherwise. So it has a cost, but our goal is to ensure that you don't pay costs that you don't need to pay. What does that mean? First thing is that we want to make sure that when you're filtering out instrumentation that you don't want to collect, that doesn't cost anything. It's nearly free. It's a single load, single branch. And then we have, so under a nanosecond, just like the log crate, single branch to skip something that's disabled. Furthermore, we can cache the evaluation of the actual filter that determines if something is disabled. So sometimes you might have a regex or something that is relatively expensive to evaluate to determine if some span or event is enabled and you want to collect it. In cases where the filter will not change, the subscriber has the ability to tell us, this filter will not change. I never want to see this. We never hear from it again. We don't have to run the regex every time to get the same result. Similarly, if you always want something, we don't have to ask every time to make sure we always want it. This is actually one of the cases where we outperform the log crate in some of the benchmarks that I've done, is at lower levels of verbosity, we significantly outperform the log crate because in some cases it reevaluates filters where tokio-trace doesn't have to. We also have compile time disabling. Well, we don't actually yet, but we will. It's quite easy to add. PR's welcome. But we can do it very easily. Second, and I think the more important thing, is that subscribers don't pay any costs by default. So you have a lot of wildly different use cases that subscriber implementations might fulfill. You might be doing some formatting like what we saw before, where you have these contexts that are associated with your spans, and you want to print those contexts every time an event occurs in that span. If you're doing this, obviously you have to do some form of allocation to store those formatted strings in, right? But we don't inflict that allocation on every subscriber. It's up to the subscriber to choose to perform that allocation. If you are writing directly to standard out and you are never going to want to write the formatted representation of a span again, we don't store it for you by default. Similarly, a lot of people like their logs to have timestamps, but not everyone needs their logs to have timestamps. If you are performing time-based profiling, you will want a lot of timestamps. You will want to timestamp every time a span is created or entered or exited, and so on. If you are printing log messages, you might only need to timestamp events. And depending on where your timestamps are coming from, you might have some internal clock, or you might want to make a syscall every time you need a timestamp. Those are all overheads that tokio-trace does not actually make for you. You get to choose how you want to generate timestamps, whether you want timestamps. We don't put timestamps on anything. What we have done is that we've made sure that when you hit an instrumentation point, the subscriber sees it right away. It's a single function call. The time difference is small enough that if you take a timestamp, then your timestamp is fine. That's all we've done. You're responsible for deciding how timestamps are taken. So we made sure that subscribers don't pay the costs that they don't need for their use case. If you want to implement buffering, you can implement buffering, great. So on and so forth. So I have a few more demos of some cool stuff that we can do. Some of them are pretty cool. And so I'm going to exit my presentation for a moment and switch over here back to the terminal that I had earlier. Where is my mouse? It is someplace. It's
look at your screen. It's easier.
Well, it's not mirrored. I wish it was. It would be much easier for me if it was mirrored.
There's a lag on this display.
There we go. Okay, here is my terminal. So we're looking at this hyper echo example. Remember how I said I'm going to kill the server? I think I would kill the server if I was in its terminal. It sure does. That's what I'm learning. Wow, I really thought this was not going to be the part of the demo that... I just want to be in the terminal where the server is running. I just did that. Okay, so I'm going to kill this guy. And I'm going to make a new one. No, I don't want that. So I'm going to rerun that example, but I'm going to add one thing. Let's say we're running this, Echo server. We're running it in production. Something goes wrong. Our Echo server is misbehaving in some way, and we think the bug might be in the protocol implementation. Let's say we want to get all of the logs that Hyper has. So remember how I said that we can consume log records from our dependencies as tokio-trace instrumentation, even though our dependencies are not using tokio-trace. So I have, again, not modified Hyper at all. I have not touched Hyper. I promise. I'm pulling it from crates.io just like everyone else. So if I say rust_log equals Hyper equals debug, and I run the sample server again, and it's listening just like before. Now, what happens when I curl localhost on port 3000? Okay, and I'm going to close my second terminal. Look at that. Where did these messages come from? Yeah, they came from Hyper. As you can see, here we have different modules in Hyper that log these records, and we can infer from the indentation that those records are inside of our trace tree. So we can pinpoint when a log line from some dependency happened within the trace tree with the spans defined by our application.
So can you get the line number in there?
We could. I'm not printing it.
And did you get the file name, the module name?
Yep, we have all of this metadata as well. I cut it all out for the purpose of the demo because...
I just want to know how you got the function name, because I was unable to...
Oh, we have a module name. We don't have a function name.
Oh, okay.
We record all... Yeah, it turns out that in Rust, because of things like monomorphization, it's hard to get function names. Yes. Yeah, it's not fun. Okay. These are modules. But we have all of the same metadata that the log crate records. We have that about all of these spans as well. I'm not printing it here because I wanted to keep these lines as short as possible because I wasn't sure how big the screen in the demo was going to be. Again, this is a special formatter that I wrote just for the demo. It doesn't have all of the information that we're recording. I can show you what that looks like in a moment. And, of course, this works for any of my dependencies. So I happen to know, that's not what I want. I happen to know that Hyper is also using Tokio. So let me just reuse the command I just typed. So I'm setting Hyper at debug. Let's go ahead and set Hyper at trace. We just really want to get the fire hose here. We want Tokio equals debug. So already I see, okay, Tokio's reactor is doing some stuff. Great. And it's doing that just in the context of my server thread. I'm going to curl the endpoint again. I'm going to curl one of the fancy ones. I happen to know that there are some secret features in this example server So I want my text backwards. So I'm going to curl echo / reversed. Hello. Okay, whole bunch of stuff happened, but I'll kill this and I'm going to just use the cursor. Oh no, not what I want. My mouse pointer is having fun wherever it lives now. I don't know where it is. It's in Google Hangouts someplace. But if we were able to scroll up, pretend that we can scroll up. When we scroll up, we will see that some of these log messages from Tokyo, some of these log messages from Hyper, all exist at different places in the trace tree because we're able to consume all of the instrumentation in our dependencies, even though they're not using tokio-trace. So that's fun. Some other stuff that we can do. I want to show off an example of the kind of filtering you might do. So I've written another library on top of tokio-trace. This is a bit of a yak shave, actually. It's kind of a funny story. And it's called tokio-trace format. And tokio-trace format is basically nvlogger for tokio-trace. And the reason is because I wanted to print spans before targets. And in nvlogger, you can't put anything before the target. You can customize the formatting, but the target always comes before anything that you want to put in. And I didn't like that because I wanted my spans to line up because I wanted to be able to see what spans we were in just based on alignment. And nvlogger wouldn't let me do that, so I rewrote it. And we can do filtering with an environment variable just like nvlogger. So I'm going to run a quick example. Actually, I'm just going to run it without any environment variable first. Yet again, this example is drawn from the fast-paced world of yak shaving. So, okay, we get back an error because error is the only thing that's on by default. Great. But just like in the nvlogger crate, we can say we want to get some more logs. So let's say rust log equals and we run it again, we see some logging now. And so this is the way that this crate formats our spans. You see at the side after the severity, we have a shaving yak span, we have a shave span. This is basically the example I showed you earlier. And so we see some messages. But this is where it gets really neat. I happen to know that hidden in this example program, there is another target. There's not just the yak shave target, which is the module path. There's another logging target that's called yak events, which I've hidden in this example specifically for this purpose. So let's say we want to enable some yak events, but we only want to see the yak events that happened inside the shave span. How would we do that? Well, nvlogger can't do that, but we can do that. We can filter by spans as well as by targets. And our filter syntax is a superset of nvlogger. So if you have like some bash script that runs your program and it sets this environment variable, it'll still work. But now we've added some stuff. And one of the things we've added is this syntax with square braces. And in the square braces, we put a span name. So we might say shave, which is the name of a span. And then now we've set the trace level for that whole span. And you might notice that we now have these yak events that we did not have before. So, and you might also notice that we filtered out everything that wasn't happening inside the shave span. We're only looking at spans named shave. We can do that. And we can also have a target filter. So we can go back here and we can say, let's say I only want to see the yak events. I don't care about the other events that are just floating around in my main. So I might say yak underscore events. And now I'm setting a log directive that is filtering both on a target and on a span. I hit return. I only get that. Okay, so that's some filtering. And I see we have some questions from the audience, so I'm going to stop and answer those. Yo, Adam, can I get you to Do the mic. Run at him. I have a lot more stuff to show off, but I'm happy to just start answering questions.
This will be quick. With the first example,
Yeah.
can you make it print the path to the shaves? Presumably, you can get to the shaves by different paths.
What do you mean?
Well, you filtered it so you're only printing things that are within the shave span.
Right.
But
so
presumably, there's a number of different ways to get to that shave span.
yeah. So we could also enable all of the parents of the shave span. The filters that I've written for this crate don't support that, but it's definitely something that you could build on top of tokio-trace's filtering API.
Okay.
This is quite simple.
We're doing more questions now.
I'm seeing a lot more questions, so I'm happy to answer them. This is basically the end of my demo. I have some slides on how you can get involved, but if nobody wants to see them, I can just sit here and answer questions all day. All right, I will do it. All right.
So I needed this 2 years ago, and I looked at
Glad to hear
I looked at Tokyo and I couldn't figure it out. I was about 3 months into Rust programming.
Okay.
So I rolled my own.
Yep.
And my concurrency is all done with threads.
Mm-hmm.
Can I use this with threads?
You certainly can. So tokio-trace does not require Tokyo. It's actually kind of a misnomer. It's actually called that because we want to use it in Tokyo. It has no Tokyo dependency.
The other thing, when I developed this, our guy who's doing our displays for our traces wanted JSON.
Oh yeah, we could do JSON.
Okay.
There will be Serde support. We haven't written it yet. You can write it if you want. PR is welcome. But you have all the tools to have JSON.
Hi, how are you implementing basically getting the logs of the crates that are not importing tokio-trace?
Yeah, so the way we've done it is we have a logger. And we set that as the logger. And that logger, instead of actually logging, it just causes tokio-trace events to occur.
Oh, so you're messing with the AST and modifying that?
No, we just, in the executable, so if you use the log crate, you can set a global logger. And in the executable, you just set a global logger, which is the tokio-trace logger. And what that logger does is when it receives log events, it just emits them as tokio-trace events. It's just a compatibility layer. We've just ensured that the APIs are compatible enough that it's easy to have that compatibility layer.
So I have a question. Do you have plans for cross-process flow event type stuff?
Yeah, that's a great question.
Okay.
It doesn't exist yet, but again, one of the big goals of the subscriber API, and also I think the reason that there's some stuff that some people are surprised by in that interface is because we want to support that use case. So I have some thoughts on how we might do this, but we give you the tools to build it. PR is welcome. Otherwise, watch this space. We might see stuff like that eventually.
Do you have any thoughts on automatically generating unique flow IDs across processes?
So to an extent, the main use case that I want to support, that I've been thinking about the most, is supporting a distributed tracing system where requests are coming in with IDs. So tokio-trace would not be responsible for generating them. Tokio-trace also has a concept of a span ID internally. I think we've determined that you probably would not want to use the distributed system span IDs for your internal IDs. And I have done some thought on how you might correlate an existing span ID in the distributed system with a span ID in tokio-trace. But we don't currently have hooks for where you might generate span IDs, but there are places where you could do it quite logically, and you might record them in a number of ways. It's really up to you and up to the system that you want to interface with. This is also something where it's important to not enforce one way of doing it. Like, for example, tokio-trace's span IDs are 64 bits because that's plenty for one address space. Definitely not plenty for a distributed system. I happen to know that all of the popularly used distributed tracing systems have, I think, 128-bit IDs, depending on what the ID identifies. So there's, David wants to know, I see, if we can share those thoughts. I couldn't see his whole message. I think some of them have been posted on a variety of GitHub issues. Otherwise, I would like to write them up at some point. Do we have
the messages from chat? Do you want me to?
why don't we finish any burning questions, and then I would like to show the last 2 slides, and then I can just sit down and do Q&A for as long as we want.
So David Barsky's question from the chat room was, can you share those thoughts on correlating between a distributed system and a trace?
So I think there are several ways you might do it, but I think the best way to do it is for the library that implements support for the distributed tracing system would provide some function that you would call with a span ID and with whatever the ID in the distributed system is. And then it would inform the subscriber that you've written that is listening to trace events that this span ID in tokio-trace is correlated with this ID in Open-Zipkin-Jaeger census. And then it would do whatever is necessary to associate that. So it presumably has some local storage that it stores that in. And when you see events and you emit them back to the distributed system, you use the distributed system's ID. We're working on a downcasting API for, so something we're working on is, and this isn't in core yet, but it will be soon, is a downcasting API for the trace subscriber. So you can get the current subscriber and actually see, is it the Open Census Jaeger Zipkin one? And if it is, then you can call methods on that are not defined in the subscriber interface. Some influence was taken from traits like standard error in Rust. The error type has a downcasting based API, and we've actually learned some what not to do things from recent like changes to that downcasting based API. There are problems with downcasting. Ours should hopefully be usable. And we've also wanted to ensure that a subscriber that's composed of multiple sub-subscribers, so if you have a T or something, that you can expose any of your components and downcast to any of them and permit us to call methods on your components. The global subscriber is basically a trait object. So the downcasting stuff is not here yet, but we can do it in a future-proof way. Right now, all subscribers have to be object safe. So there's everything we can do, or everything we need to do to implement the fully featured downcasting system doesn't require any breaking changes. We can do it in a forwards compatible way. So that's basically how I think you would go about implementing some correlation between a distributed tracing system and tokio-trace. I hope that answers your question, David. He hasn't said anything, so we can assume. Should I show the last 3 slides and then we can just do Q&A for a while? All right. I do actually have a couple more demos, but we can get into them later. So I'm going to get out of my terminal and get back to my slides. And finish them. I'm still in the terminal. That's cool. Computers are great. Huh. I have not seen this. This did not happen last time. Oh, okay, here we are. We're back here. We've seen all of these slides. We've seen some demos. And I think this dovetails into a lot of the questions I'm getting from folks in the audience. And the point is, we are trying to bootstrap an entire ecosystem of libraries here. So we just released the core library, tokio-trace core, on Crates.io actually this morning. I finally got Carl to push the release button for me. And that's just the beginning of what we can now do. There's a whole lot of neat stuff that we can build using these tools. And I think one of the biggest design goals of tokio-trace is that it's not a logging system or a tracing system or a metric system. It's a set of tools for building metric systems. It's a set of tools for building logging systems. It's a set of tools for building tracing systems. And there's really a lot that you can do on top of it. And I'm really excited to see all of the code that people write. I probably haven't even thought of all the things you can do yet. And we've designed all of the API service to be extensible and composable and to permit you to do whatever your use case requires. So how can we get involved? Here's some places to go. The first thing you can do is just try it out. You can try it out. The core crate is on crates.io now. The tokio-trace core and the instrumentation API, which is the tokio-trace crate, live in the tokio-rs/tokio repo. And then we have a nursery repo that has all of the fun stuff that's less stable. All of the leaf crates, the actual subscriber implementations for doing different things that I've written so far live there, and some utilities, some compatibility layers, and some neat stuff like procedural macros for the real Galaxy brain folks. So I love bug reports. I love feature requests. I especially love pull requests are the best, but I'll take what I can get. So please try it out, and if anything doesn't work, let me know. I like that. Second, if there's something you want to see in this ecosystem that doesn't exist yet, please share that idea. I would love to see what people write, but even if you don't have the time or you don't understand all of how something might be implemented, please share the idea, and someone will probably pick it up because odds are someone has the same needs as you. So please talk about what you want to see and what you want to be able to use, and someone somewhere will make it happen. Could be you. And finally, I wanted to say thank you to some folks, a lot of whom are with us virtually tonight. Carl, obviously, is the original author of Tokio, and none of this would have happened without Carl. He provided a lot of really valuable guidance throughout this process. David Barsky, we had a lot of really great conversations. He helped develop the design of tokio-trace, and he wrote some proc macros that I was going to show off but didn't. I still can. Ashley is working on an RFC to add structured logging to the log crate. We had several good conversations about how to do that in a way where tokio-trace's structured logging is compatible with the log crate structured logging, and he influenced the design of how we actually represent values, which was really valuable. And Lucio helped out a lot with the nursery crates, and I think he's here tonight too, so thanks, Lucio. And of course, thank you to everyone who's listening tonight. Thank you to my partner, Tristan, who let me try this talk out on them like 4 times, even though they have no idea what I'm talking about at all. And hopefully, if I give this talk at RustConf, I'll be saying thank you to some of you in the audience right now, too. So if you have any questions, I'm actually going to sit down and do Q&A again. But before we do that, here is how you can contact me. Is my email address, my Twitter account. These slides are already posted on my website, or see me after class. I love to chat about tokio-trace, Tokio in general, or Linkerd, which is the other thing I do. I think we brought, my employer brought a bunch of shirts, but I think they might all be gone now. Get them while they're still there. We have stickers too. And if you want to take a picture of this slide so that you have all of this information or where to go to get all the rest of the slides, I've been told that's something that people do. And now I'm happy to answer questions all night if you guys want. I love talking about this stuff.
Thank you, Eliza. I'm going to shuttle the microphone for like 15, 20 minutes before I go eat more tacos. But
I think we have also some questions from remote folks.
No, they're bringing them back.
Oh, okay. We might have more questions from people who are watching. Oh, I should take that mic. Yeah. Smart. Okay. Thanks. Can you all hear me okay? I think I just turned this off. Can you hear me now? Yes. Okay. I see a question from Ashley, but I'm going to let everyone who is in the live stream know. I'm going to let everyone in the live stream know right now that when your questions come up, I only see about the first 5 words of them. They're getting truncated. I asked Adam ahead of time if he would. What are my thoughts on immediate next steps for tokio-trace?
Sorry, everyone.
Yeah, so I asked Adam if he would be a stand-in for everyone who is not with us in the flesh, and he's here now, actually. So why don't you come help me with that? So Ashley wants to know what immediate next steps are. Immediate next steps are probably stabilizing the instrumentation API. Right now, the core API is stable, but the API, the tokio-trace proper crate, which is where the macros live, most of the macros, there's a lot of macros. Most of the macros, not totally stable. There's a little room for API polish. The goal was specifically to get the core API stable because we don't want to change it because it needs to be, you need everyone on a compatible version or else they can't talk. And so we tried to minimize the surface area of what changing or of what code that we don't want to change ever again. Or it would be pretty bad if we did. Oh, Adam is here again. Okay, great. So that immediate next steps, the instrumentation API should stabilize. We have a summer of code project in the works right now for something that, this is what Carl's talking about in the chat, Tokio console. And the idea is that we want to have an out-of-process console that you can connect to a running application that's using Tokio, and you can consume all kinds of instrumentation data to try and diagnose what's going on at runtime. And we're building that using tokio-trace instrumentation, but it's going to be out of process. So you might be able to get the Tokio console on your machine to talk to some end nodes in a distributed system and see exactly what's happening in the Tokio executor on each of those machines. And that's currently a summer of code project that's going on. Other next steps, or I think most of the questions are going to be about next steps in some way or another, unless they're about the implementation. Sorry, let's keep answering questions.
This might be related to what you just mentioned about a console. I was interested if there's a possible API hook for runtime changing of the log level or the filtering, because that would allow for a nice feedback loop.
For sure. Yeah, so that's something that the subscriber API is really designed around the idea that you might want to support runtime changing at the log level, or you might want to support dynamic filtering. So we basically have a two-step process for how subscribers do filtering. There's a register call site hook, and that's called every time we have a call site, and those are static. So every subscriber sees every call site exactly once, and at that point it gets to say, I want this or I never want this, but it also gets to say, I might want this, ask me again when it happens. So a call site is the instrumentation point. It's where either a spanner event lives in the source code. We call that a call site. And the subscriber can say ahead of time, I don't ever want to see this, never talk to me again, or it can say, I'm opting into this all of the time, always show it to me, I don't want to filter it. But most of the time, it's not going to say either of those things, so it has a third option, which is right now, it can say, I'm sometimes interested in this. And when you say that, your filter will be reevaluated every time we hit that call site. And if you want to support dynamic filtering, that's one way you might do it. Another way you might do it is you might replace your subscriber every time its filter changes, which would let you benefit from some of the caching that we're doing. But then you would invalidate the registry of the previous subscriber. And so then switching subscribers might have a little overhead, but you're not going to do that nearly as much as you're going to filter a call site. So there are a few approaches we could take, but it's definitely something that the current subscriber API permits, and that's really the goal. More questions. Henry, I see you there. Have a microphone.
So I don't know that much about distributed systems, but in one of the things that you mentioned where you have like all these different pieces of software that are all logging and there's some log aggregators and stuff, if those different components are operating in like different kind of security compartments, does it make sense to try to like build some kind of like secure logging system into tokio-trace, or does that like not make sense?
I mean, I think that the security is a concern of how you would actually be communicating with that aggregator. So if you want to have, if you want to have an encrypted communication with that aggregator, you would have some layer of encryption, and that would be in whatever the actual code for communicating with the aggregator is. So tokio-trace itself doesn't define one method of communicating with an aggregator. It might be over HTTP, it might be over TLS, it might be over just writing some bytes into a socket using Henry's homemade encrypted protocol. It might be some blockchain thing that I don't understand. And you can plug any of that in to the subscriber interface. It's really once an event hits the subscriber API, the ball is in your court. So you can do whatever you want with it. And that if that means, doing some crypto magic, then you can do that. There's nothing stopping you from doing that. Does that answer the question? Sorry.
Hey, so a thing that commonly happens, I've noticed with async programming, is that my server is happily running and doing things, and then everything stops. And it's gotten to some sort of deadlock. And what I really want to do is be able to poke around and find out what its current state is. But if tracing has been disabled, is there still a way I could be able to get a sample of all of the current states of the span stacks and explore the process that way?
Right. So actually what you're describing, first of all, is basically the use case we have in mind for the Tokio console project.
Right.
But again, I think I mentioned before, the filtering is up to the subscriber implementation. So if you want to permit that kind of use case, you're going to need to never flat out deny all of the instrumentation, because it can't be, if you say you don't want it, you don't want it. So it can't be collected then. So you might still want to collect some of it and not record it in, not actually output it, but just record that, that this has happened. And then when somebody requests, hey, I want to know actually what's the entire state of this machine, please dump it, you have something to tell them. You can't really have that otherwise without actually inspecting the binary that's running and looking at the call stack. And that's a much lower level concern than what tokio-trace supports. I would use GDB for that, even though I've been told I shouldn't.
Right. But specifically with Tokio, where it's async, and you have a task that has decided that's going to block on some IO, or not block on IO,
Right.
and then it returns its call stack, and there's nothing left behind of that task until it gets run again. And Tokio at the moment doesn't, I think, have a way of doing something at the moment that you register that task with some, I forget what, a waker? Is that the terminology? I think it is.
A waker.
And so would there be a hook in Tokio that allows you to have an event attached to the waker, setting a waker or something like that, so that you have a moment to record that information?
Carl has something to say, I see, that you wouldn't want to do it in production. I didn't see the beginning of Carl's message.
Carl says, this will be possible, but tracking the data will be, quote, expensive.
Yeah, that was really what I was getting at before, is that if you say that you don't want to collect any instrumentation, you are actually not collecting it. You can go back in time and collect it. With that said, you might want to collect a smaller amount of information all the time than what you might be collecting if something has actually been opted into, just in case you need to respond to some kind of diagnostic request like that. And I think that's a totally valid use case. But you would need to, you would care about what overhead am I adding by storing all of this. Okay. You have to do that.
Yeah, thanks.
Yeah, I hope that answers the question.
Sorry, I had two questions. I hope that's okay. The first one should be quick. So does a span trigger an event when it starts and when it ends?
So the problem here is really that event is a pretty overloaded term. It's used both to refer in the general sense to something that happens, some kind of event, and also to a specific type that we have in tokio-trace's API that represents a subset of events. So when a span is entered, when it's created, when it's exited, and then when the span has closed are all stages in its life cycle, and the subscriber gets notified about those. Those don't actually cause events, although we can think of, they are events.
Sure. Okay.
The biggest problem is that sometimes I've been known to say trace events to refer to spans events and all of the span lifecycle events, but event is also the name of a type. The problem is that I could not think of a better name for that type that actually described what it represented. But yes, all of those things are things that you can collect. Sorry.
Okay, Claire. My second question is, do you have any thoughts on preventing accidental inclusion of sensitive information in log messages?
Don't do that then. For real, I would say our structured logging actually helps with this a bit. You're recording type data, and the data itself in the future, we'll have some more control over how it wants to be recorded. So we have a trait value. Right now it's sealed. It might be unsealed soon. And you can implement value for your types, and they get to define how they wish to be recorded. So if you have a type with sensitive data, you might have a value implementation that doesn't record the sensitive data. And now you might just you might provide that. And even if you're a library, your downstream users get that value implementation. So they can't accidentally record all of the sensitive data that's stored in your struct or whatever. Right now that's sealed because we want to work on getting the API forwards compatible, but it may be unsealed and available for arbitrary types to implement in the near future.
Quick two-part question. You said earlier that you named it tokio-trace because you wanted to use it in Tokio. Do you mean like actually in the library Tokio itself? And that leads to the second question is, you explained that you can use like the log macros from the normal log crate, and you can consume those in tokio-trace. Can you do the opposite? If someone is using like a regular logger and not a tokio-trace logger, can they get, if you have a library that's using tokio-trace, will that still work?
So that's something that I would really like to write in the very near future. It's actually kind of the big blocker right now for replacing all of the log instrumentation in tokio-trace, or in Tokio with tokio-trace. Is the ability to expose tokio-trace instrumentation in a backwards compatible way, as well as consume log instrumentation. We do have an adapter layer that you can use right now that actually logs trace events, but it's something that the application sets up as a tokio-trace subscriber. In order to have the library actually exposing log events, there are some changes to the instrumentation API that are in the pipe. And yeah, so that's really the next step to get Tokio itself instrumented, is to be able to have to keep exposing the existing log instrumentation. That's a goal. I'll probably have it done by the end of the week, but that's probably not actually true. Ashley wants to know what that change entails. It's really just some changes to the macros in the tokio-trace crate, so that we have a feature flag for also exposed log instrumentation. And if that feature flag is set, we also expose log instrumentation. It might be an environment variable, but we'll see.
So right now I'm in the middle of debugging a message order non-determinacy that
Sounds
bites me
bad.
one. Yeah, it's terrible. 1 run out of 10. Is there sufficient information to build a replay system that would at least replay the order of the spans?
There could be, if you're collecting it. This is like our tokio-trace motto is, did I turn my mic off? I turned my mic off. I think I did. Can you hear me? Carl says you should use Loom. And actually, that's an excellent suggestion. If you have heard of Loom, Loom is a concurrency model checker in Rust that Carl has written. And it's already found some bugs in the runtime. It's a permutation fuzzer, I'm being informed. It runs all permutation. Yeah. Okay, so you have a situation where you're, yeah. So the tokio-trace motto is it's a subscriber problem. So if your subscriber records sufficient information based on the primitives that are exposed to it, you definitely could do that. But it depends on the implementation. If you're recording metrics, obviously you can't do that. You know, if you just have some counters, you can't play back all of the events that have occurred from those counters. But yeah, that's definitely something we could implement. Oh, and now we're looking at a picture of the audience.
Oh, wrong one. Sorry.
Oh God, that's me. Do we have any more questions?
Yeah,
we do.
One or two more questions. Okay.
Two more questions.
If you have a future in a Tokio future that's like, say, not ready, call back soon. Sometimes later it comes back ready. So Tokio is going to call back the same call chain, so the same span stack. Do you correlate the same the span that yield the not ready and the ready one? Is that the same span, or is that two different spans?
It depends on where you put the span macro. If you have a poll implementation where every time poll is called.
How about for the instrument?
Yeah. So this is why we have instrument, because it's really not sufficient just to put a span macro in your poll implementation. You want to have the same span entered every time the future is polled, which is what the tokio-trace futures crate does, which is why we have that instrument combinator. If it wasn't necessary to preserve the span, then you could very easily just have your future implementation put a span in there. With that said, there's a use case for both. It's sort of like David asked me a question a while ago when I had, first introduced him the concept of tokio-trace's spans. He asked me, if I have a for loop, should I put a span around the for loop, or should I put a span in every iteration of the for loop? And the answer is yes. The answer is it depends on what are you looking at. Do you want to look at the length of time that you spent in that loop, or the length of time that was spent on each iteration of the loop? Those are separate. You can put the span macro where you want it and get what you want back. But yeah, the instrument combinator enters the span every time we poll the future, because you want to think about the logical amount of time that we spent in this future when we were driving it to completion, and we only want to close that span once the future is completed. We have some more questions? I think we have at least one more hand raised, so I'm happy to do that question as well.
So with the future or standard futures RFC finally landing, are you at all compatible with futures 0.3, incompatible, pretty much agnostic except for the combinators?
So none of the futures compatibility is in tokio-trace. That all is in external libraries. In tokio-trace futures is the name of the library. I probably should have called it tokio-trace futures 01 because the current implementation was written against futures 01. But there's absolutely nothing preventing it from being used with futures 02, except that or futures 03 or futures 7.0, except that it imports the future type from futures 01 right now. The futures compat layer is really quite simple. So porting it to futures 03 is probably going to be very easy. I haven't done it yet because it wasn't stable when I wrote the futures compat label. Now that the RFC has been merged, probably over a weekend, it should be quite easy to have a futures 03 version of the futures crate as well. Yeah, does that answer the question? Cool. One more?
Yeah, hi. Is your ultimate goal to make tokio-trace the logging library? You said it wasn't a logging library, but tokio-trace.
It's not a logging library.
Yeah.
It's not just a log.
Sure. For all logging done by everyone everywhere in Rust, or do you think there's still use cases where this like log or something is better?
Well, my ultimate goal is total world domination. So, no, I'm glad you asked that question, because it's something that I have really wanted to make sure that everyone knows, that the goal of tokio-trace is not to compete with or replace the existing logging libraries. It's a part of that ecosystem. There are use cases where you need all of the extra diagnostics that tokio-trace provides you with. There are use cases where you don't. And for those use cases, you could use tokio-trace, but you don't really need to. And log works great in those use cases. The reason that we have a drop-in replacement path is really not because we want to replace all uses of log, but because most of the folks who need tokio-trace are probably using log, and we don't want them to have to break their builds while they adopt tokio-trace. So the goal is not to replace the existing ecosystem. The goal is to work with and complement the existing ecosystem, and hopefully to have a place in it.
I just want to add on to this question. You've talked about compatibility with log. There's also slog, which is like for other structured logging. Is there compatibility or plans for compatibility with tokio-trace and those logging libraries?
First of all, yeah, I want to say thanks to slog, because I looked at slog a lot, and it was a big part of the inspiration for tokio-trace. There isn't compatibility with slog yet. It should be possible. I haven't written it. I use log at work. I don't use slog. I would like to have compatibility with slog. It should be possible. But slog was a big influence on tokio-trace's design. The big difference between tokio-trace and slog, a big difference, is that we don't require explicit passing of contexts, which is the pain point that I have had working. The pain point that I have had working with slog in the past is that it requires explicit passing around of context, which is hard to do in a futures-based code. So we don't do that. But you could probably wire tokio-trace's field API into slog's field API pretty easily and get like nice structured slog logs. I just haven't written it yet. Somebody else should. I don't want to. DPC should do it.
All right.
I'm done answering questions now.
Okay.
My throat hurts.
Thank you, Eliza. So with that, we have more tacos, more beer, wine, water, etc., and about another hour where we can all hang out and do whatever.